Hello, my name is Dr. Patrick Briggs from the Citadel. During week 2 of GoSciTech, we did a week on astrophysics, stars, and galaxies. Here's what we did.
I'm Sierra, and in this class we learned a lot about graphing. So in astrophysics we have really small numbers and really big numbers. And these big numbers can be things such as suns or even whole galaxies, and the really small numbers can represent stuff like atoms. So two ways that we can compress these numbers to make them a lot smaller is by using scientific notation and logarithms. So scientific notation is a way that we compress it. So instead of having a big number like 100 million and having to write that out, we can say something like 10 to the 8th power. And here are just a bunch of examples of really small objects and really big objects that can now be represented in the same way. We also use graphs, and this is a logarithmic graph. And down here we have a green pea, and up there we have the sun. This is a very small number and a very small object that can now be put in the same place as a really big number and a really big object.
Hi, I'm Lucy.
And hi, I'm Sam.
In this picture you can see that the stars look like they're moving. The reason this is because this is our proof of how the Earth is moving. Because if you take a time-lapse photo, you can see that the stars move. In this photo, you can see that the Earth is tilted on an axis. It is at a 23.5 degree axis. It rotates around the sun in not a circle, but an ellipse, which is almost oval-like.
In these two graphs, in the top one, it shows the northern hemisphere locations for different countries or cities, and in the southern hemisphere, it shows the different graphs for countries or cities. And you can see the difference because this really shows that it's on a different tilt, and that part of it's pointing forward when the other one's pointing back, because these go down when the sun's lower, and these go up when the sun's higher. And on the Tropic of Capricorn, which is about 23.5 degrees above the equator, you can see it has a weird curve to it. And if you get really close to the poles, it'll start having a flat line where you don't see a lot of sun for a lot of the day.
This is the history of astronomy and Kepler's laws. I'm Lily.
I'm Emma. And we'll start with geocentric and heliocentric theories. This is represented by this picture. The geocentric theory explains that the Earth was orbited by the other planets, but Copernicus was a man who developed the heliocentric theory and later proved that the sun was what the planets orbited around. The Kepler's laws, which is represented by this photo, his first law was that planet orbits are in ellipses, and his second law is that the closer a planet is to the sun, the faster it revolves. And his third law is that the square of a planet's orbital period is proportional to the cube of its semi-major axis.
This graph here shows that the lower the AU, which is the distance between a planet and the sun, the lower and shorter the orbit of a planet, which demonstrates all of his laws.
I'm Ayla,
I'm Rigdon.
and for our slide we did lights and telescopes. So to start off, one of the largest telescopes in the world, they are usually reflective telescopes, which is where they use a mirror to kind of focus on images that are like farther away. Currently the largest reflective telescope in the world is the extremely large telescope in Atacama, Chile. It is like stationed here because of the dry atmosphere, and there's like very little rain there. Actually, there's no rain, so it's a very good environment for it to be there, and it helps us see farther stars that are like millions of light years away.
Using these telescopes, we can see the light that comes from the stars, and light is really the only way we can get information from stars. So using the wavelength, we can get temperature, energy, composition, and the distance of the stars. So the Doppler effect also applies to light, meaning that we can get distance based on how the spectrum is shifted, and using other math problems that many people, mathematicians from throughout history have created, you can find other things. And then these charts are of lenses and the distance between the light in the lens and the distance between the lens and the image. And this ratio comes down to be a linear line that is a really cool ratio in math problem.
Hi, I'm EJ,
I'm Becca.
and we can classify stars based off their physical traits and features. For one, stars are a very color-dependent thing. We can tell the temperature of a star just by its color. Stars that are usually hotter in temperature are blue and white, and stars that are usually cooler in temperature are red and orange, and can even sometimes be brownish in color. We can also classify different stars by these physical characteristics as well, such as red giants, red supergiants, white dwarfs, and brown dwarfs are all just some examples of the different classifications that stars can take up.
Something that we can use to help us classify stars is spectroscopy, which is when we look at the line spectra of stars. And we can use that to see what stars are made of based off the colors they emit, such as helium and hydrogen, which are both found in stars such as the sun.
Hi, my name is Salem,
My name is Owen.
and we are doing stellar evolution.
Stars start out as clouds of dust such as this that rotate very slowly circularly, and then eventually gravity presses down the cloud of dust and debris into a hot dense point that eventually becomes able to burn hydrogen, and that is called a main sequence star. After stars move out of their main sequence, they start to burn helium and expand. After this and some other stages, they expand so much that they lose their outer shell, causing a A1 supernova and usually a white dwarf.
This graph is called an HR diagram, which is how we show a star's evolution and ending physically. The middle area right here is called the main sequence, where most stars spend millions of Earth years. Once they leave the main sequence, they could grow in temperature, mass, and luminosity, but they could also shrink. They usually come over in this general area to die, luminosity, brightness, and temperature going down.
I'm Riles.
I'm B, and we're talking about high mass stars, neutron stars, and black holes. High mass stars are usually have more than 5 times the mass of the sun. They fuse heavier elements like carbon. When they die, 2 things can happen. Either they turn into a neutron star or a black hole.
If a star collapses into a neutron star, all protons and electrons are pulled in by gravity with extreme intensity. They are pulled in so violently that they fuse and become neutrons. That's why it's called a neutron star. The neutron stars are commonly have a mass of around 1 to 3 solar masses.
The biggest stars turn into black holes. These have so much gravity that light can't even escape, usually like bending around it. They also eat matter, like stars and gas, which turns into an accretion disk around it. Black holes usually have 10 to 100 solar masses.
Cepheid variables are a type of high-mass stars which pulse rapidly, causing changing levels of brightness. This pulsing helps astronomers to find where certain stars are located compared to Earth.
I'm Addie. I'm Josh. And we're talking about galaxies. Galaxies are gravitationally bound collections of dust, gas, and stars. There can be millions to hundreds of billion stars in them. We talk about 3 specific types of galaxies: elliptical, spiral, and regular. Elliptical have hotter gas, an orange to red color, older stars, and are more point-like. Spiral galaxies have cooler gas, hotter stars, newer stars, arms, and a central bulge. Irregular have neither and are caused by spirals colliding and taking stars from each other.
Also, galaxies are slowly moving away from each other, and 90% of matter in galaxies consists of dark matter. Galaxies have dark matter halos around them, and dark matter is an unknown particle-like material around galaxies that doesn't absorb, reflect, or emit light. Is most likely made out of WIMPs or weakly interacting massive particles. And finally, the closest galaxy to the Milky Way is Andromeda. It's 2.537 million light years away.
We want to say thank you to our instructor, Dr. Briggs, and to our student assistants, Eva and Will. And thank you to our parents for bringing us to GoSciTech. We had a great week.